Welcome back to The Explainer. Today, we're diving into a groundbreaking new theory that might just be the key to unlocking one of the most sought-after technologies in physics, room temperature superconductors.
Sounds like a weird riddle, right? But the answer gets at a single, incredibly powerful idea that explains the difference between an insulator, a regular conductor, and, you guessed it, the holy grail of material science, superconductors. And this idea might just unlock a future we've only dreamed of.
Okay, so here's how we're going to break it down. First, we need to understand this core concept called the electron tunnel. Then we'll look at the one number that controls everything. After that, we'll see how this idea cracks open the biggest mysteries about superconductors. We'll zoom out to see how it all fits together, and finally, what this means for actually building the future.
So let's start with the big idea, the thing that ties this all together, the electron tunnel.
Okay, so picture a block of concrete. You got all the little pebbles, right? Those are like the individual molecules, and electrons are normally just stuck there. But the electron tunnel, that's the cement that connects all the pebbles. It's a continuous network, a shared pathway that lets electrons cruise across the entire material. And this, right here, is the game changer. A material's electrical properties aren't some fixed thing. It all just depends on this electron highway. In an insulator, there's no highway. The roads are all dead ends. In a conductor, there's a highway, but the electrons have to pay a toll. They need a little boost of energy to get on the on-ramp. But in a superconductor, the electrons are already on the highway, flowing with absolutely zero resistance. So if this electron highway is so important, what actually builds it? Well, it turns out it all boils down to just one key variable. Scientists call it C, the attraction coefficient, and it's basically just a number that tells you how sticky the molecules are to each other's electrons. The stronger that attraction, the more likely they are to form these incredible electron pathways. Okay, now this graph is where it all clicks into place. See that horizontal black line in the middle? Think of that as our magic line. If an electron's energy is above that line, it's free, it's in the tunnel. If its energy is below that line, it's trapped.
So let's look at that blue curve first. Here, the attraction, C, is 0. And look, the electron's energy is always negative. It never gets above the line. That electron is totally trapped. That right there is what a perfect insulator looks like.
Now, check out the red curve. We've cranked up the attraction just a little bit. And boom, a narrow tunnel opens up where the curve goes above the black line. This is your everyday conductor, like a copper wire. Electrons can flow, but they need a little push, an energy boost, to make that jump into the tunnel. That effort, that's what we feel as electrical resistance. And then, there's the yellow curve. This is where the magic really happens. We've maxed out the attraction. Now the tunnel is super wide, and it's so close to the molecule that it actually overlaps with where the electron naturally wants to be. The electron doesn't need to jump anywhere. It's born onto the superhighway. That is a superconductor.
So this is a really neat idea, right? But does it actually explain the bizarre things that superconductors do in the real world? Well, you bet it does.
You've probably seen those incredible videos of magnets levitating. That's called the Meissner effect, and this theory explains it perfectly. As the electrons are cruising through their tunnel, an external magnetic field tries to push them. But as they get deflected, they create their own magnetic field that pushes back with equal force. It's like a perfect invisible magnetic shield that causes a levitation. But there is a limit. If you hit the superconductor with a magnetic field that's just too strong, it physically deforms the space where the electrons live. It squishes their orbitals, kind of like crushing a paper lantern. This can actually pull the electrons down and out of the tunnel, destroying the superconductivity. And poof, it's just a regular conductor again.
This also explains the weird behavior of something called type 2 superconductors. See, these are often made from alloys, which means their electron tunnels aren't all uniform. Some spots are wider and stronger than others. This lets them exist in a mixed state, where a magnetic field can punch little holes or vortices through the weaker spots, while the rest of the material stays perfectly superconducting.
And you can see that progression right here. In image A, the field is weak. All the tunnels are open for business. It's fully superconducting. In B, the field gets stronger and starts to poke those little holes through the weak spots. And by the time we get to C, the field is so powerful, it's just crushed all the tunnels, superconductivity is gone.
Okay, so let's zoom out for a second and look at the bigger picture. How do things like pressure and temperature fit into all this?
You know, this might be the most profound part of the whole theory. We usually think of a material as being an insulator or being a conductor. But that's not really right. They're just different states of the same matter, just like ice, water, and steam are all states of H2O. This means an insulator isn't just an insulator forever. Under the right conditions, it can become a superconductor.
And this diagram is basically our map. It shows that superconductivity isn't some bizarre, exotic phenomenon. It's a completely normal state of matter that most substances can enter. It just so happens that for most materials, you need really, really high pressures and incredibly low temperatures to get there.
And when you think about it, it makes perfect sense. What does high pressure do? It literally squeezes the molecules closer together. That strengthens their attraction and widens those electron tunnels. And what does chilling a material do? It causes it to contract, which, you guessed it, brings the molecules closer together. Both methods help build a better, wider highway for the electrons.
So what's the big takeaway here? What's the point of all this? Well, the theory of electron tunnels doesn't just explain how things work. It gives us a practical guide, a roadmap, for actually engineering the materials of the future.
The search for a room temperature superconductor is no longer a random guessing game, just mixing chemicals and hoping something works. Now it's an engineering challenge with a clear checklist. We need to arrange molecules to create that compression for wide tunnels. We need to pick elements that are good at sharing electrons. We should keep the structures clean and simple so the tunnels can connect easily. We can even mix different sized atoms to create those helpful internal pressures. The hunt is over. The design phase has begun. The electron tunnel theory has given us a completely new map for the future of material science. The quest has shifted from one of blind discovery to one of deliberate design. The question is no longer if we'll get there, it's when. So with this new roadmap in hand, how long do you think it'll be before we engineer a world powered by this incredible technology?